Hello fans of geometric methods, welcome back. This is a fun, quick tutorial on getting the bending moment at some cut in any of the members of a space truss or a space frame, I guess, because you must question why on earth would there be bending in a truss. If the loads are applied to the nodes, there is no bending. However, self-weight. So if self-weight is present, as it is in your structures, then bending will occur. And there's only one equation in the whole book, unknown times delta, and the unknown is the moment. Thus, the delta is the rotation here. Plus each force times each loft equals 0. So let's go through the PowerPoint real quick here and see the strategy. The strategy is, I'll zoom through the slides and then we'll return back to GeoGebra. The strategy is establish an unambiguous crown, the intersection of a circle with 2 spheres or the intersection of 3 spheres. You know how to do this, right? Okay, so get that. You can in fact take your old script, set delta equals to 0. If you had a delta on the bar as an elongation, just set that equal to 0. Rename that as delta axial because now I need to use delta for the angle. Okay, so that's easy. The next question is, how does the strut bend due to its self-weight? And here's the question is, what's the strong axis or what's the weak axis? If it's a circular cross-section, I think we're in luck. But if it's a rectangle, you need to align the axis of bending. And certainly we could handle biaxial bending here. So I'm just going to pretend that the bending is along this line, but normal to the cross section on a horizontal plane. I don't know if that makes any sense at all. I'll show it to you geometrically. So what I need to do is drop a vertical plane here. Now I know that that plane will capture A and crown 1, but I need a third point for a vertical. So I could have passed a vertical line through crown 1 and seen where it pierces the ground plane, but I chose to drop a vertical line through the midpoint of the strut and detected where that line pierces the horizontal plane, just because I need this point anyway. So that's why I did that. Once I have a third point, I can create a plane, 1, 2, 3. Doesn't matter what order you do it in. And I have a plane that is perfectly vertical on that stick. Now, it doesn't have to be perfectly vertical. If your member is rotated along its axis so that it's biaxial bending, then you could create a skewed plane. But for me, I'm going to just drop it vertically here. Now, why do I need that plane? What I'm going to do is crack the beam, which is this member A. I'm going to crack it, and I will deform that into 2 halves. One half will be up to a certain point, and then the second half will be to the new crown. But that perturbation must be in this plane. It must be contained in this plane. And I'll show it to you in GeoGebra. Once you have that circle, you drop a point on here, and we'll call that mid A prime. And that length from A to mid A prime has to be this strut length over 2. And then another intersection will give us the crown, the new crown. So here, that's exactly what I did. I have a strut that's not shown here going from A to mid A prime. It's constrained to move on that circle. Then I created another sphere of radius, the length of A over 2. That's this sphere. And I find where that intersects is the original sphere around B and the original sphere around C. And that's my crown 1 prime. once I have crown 1 prime, you'll see that the problem is essentially done. All I have to do is figure out the lofts. But let's talk about the lofts. What are the lofts here? So now we'll go over to GeoGebra and perhaps start visualizing this one more time. So I cracked the tripod in half, strut A. I cracked it in half. And the angle, the delta, is the relative rotation between the two sticks, such that when it's unperturbed, that angle is 0. So how did I do that? That's not hard at all. You just draw 2 lines here, a line from A to mid A prime, a line from mid A prime to crown 1 prime, and then just get the angle between these 2 lines. It says select 3 points or 2 lines. So you get that angle. That's really quick. How about the perturbation of the shape inducing lofts? And that's exactly what we're going to look at now. For instance, do these sticks on this side of the crown, do they contribute to the bending? And this is the best part of this tutorial, I think, because the answer is no, they don't, but it sure looks like they do. And the reason why it looks like they do is this, that if I put the weight of strut C at the midpoint of strut C, during this perturbation, that midpoint moved. You could see it move vertically. Move vertically a lot. Look at that. Okay? And if that's moving, that would be a force times a loft. And similarly for strut B, that would be a force times a loft. However, that doesn't make any sense. Like, how could the self-weight of these two bend this? And the only way that is true is if there's an eccentricity of the load path. So if it's arched on this side, and if you took the other course, you know exactly what I mean. If it's arched, it's off of this funicular line, and then there's bending. It's a great lesson. But this is a secondary effect, a second order effect. It's a P delta effect. We're, what we call in nonlinear mechanics. So it's the force at the eccentricity from this line to the cut. That's so cool. But of course, the second order effect disappears for very, very small perturbations. And for large perturbations, it's there. It's a great visual tool. I don't think anybody's done this, but you can explore it. So let's get back to the PowerPoint here. For small perturbations, there is no second order effect, and we get the work done only by the load on stick A. The load on stick B does not contribute to the solution. The load on stick C does not contribute to the solution because those lofts disappear. Those lofts disappear. Even here at 7 degrees, you could see that those lofts disappear. Now, what about the other loft on stick A? Those must be here, and you cannot just put all of the load on the kink here. In the book, in chapter 2, anytime you have a kink, you must proportion the load to either side of the kink, and that's exactly what I did here. So I took half of the load of strut A and put it on the quarter point, or half of the half. And then I took half of the load of strut A and put it on the quarter point, or half of the half. And now all I'm doing is tracking the vertical movement of those two loads. So from A1 to A1 prime, I'm just capturing the difference in Z values. From A2 to A2 prime, I'm just capturing the difference in Z values. So it looks like C1 and C1 prime have a component, but they don't. It's actually 0. So you could do this geometrically, or just type it in just to capture that loft. And here's the answer. This is a finite element program, 292.6. And for a large perturbation, I get 187.7 force length. That's self-weight. I just put in a self-weight here. And then when the perturbation gets really small, I get the exact answer. Now let's go back to the final big insight here. I made a tripod with material that has some weight. I call that my strut. But on the tripod on the right, I made a my zero strut. So that is a weightless strut. So here, this one has weight. This one does not have weight. But the other two have weight, okay? What would be the bending moment in this member here, the my zero strut? For the small displacement case, no second order effect, what would be the bending moment in this strut for self-weight? And the answer is 0, of course. There's no bending in here. And furthermore, there's bending in these two because of self-weight, but they cannot transfer that over to this member. It's impossible. It's physically impossible. It's going through the crown, and the line of action is along this line, so there's no bending. So it's a great lesson. I hope you enjoyed it. It highlights this second order effect, which is super cool. I wish we could study this a little bit, but I don't have time to study it right now. It's essentially an algebraic solution of WL squared over 8. Nothing magical about that. All you got to do is get the correct W and correct L. But we did this in a super fun way, highlighting load flow ideas and just having some geometric fun. I hope you liked it.